Okay, today we're going to start Unit 7 looking at similarity and transformations. We've talked about transformations before. Specifically, we talked about translations, rotations, and reflections. But today we're going to talk about a different type of transformation. If you'll remember, each of those transformations had rigid motion, meaning the size and shape of the figure was not changed. However, today we're going to notice that what happens when we dilate an object. Kind of the key word there is it's going to be stretched. Looking at this right here, if we were to stretch A, B, C, D by a factor of 3, then A would be located in the diagram shown below. Basically, we're going to multiply the length from the origin to A times 3, and that will be our new point, our stretch point. A dilation is a type of similarity, transformation that enlarges or reduces the original figure. Key word here is proportionally. That means that it's going to be the same proportion. If we dilated in our example right here, if we dilated A 3 times, we're going to dilate B 3 times, C 3 times, and D 3 times. It's never going to be 1, 3, 1, 2. It's always going to be the same amount. Okay, the stretch point is the center of dilation. In this case, it would have been that origin. And the enlargement reduction factor is the scale factor. What that means, the enlargement reduction factor is, our example with A right here, we said how many times? 3 times bigger. That would be my scale factor, 3. Okay. How are the 4 shapes different? How are they the same? So what we're going to do here is we're going to actually going to transform this figure. So notice that if my origin was here, I'm going over 3 up 2. So that is the length. So if I'm going to stretch it 3 times, that's going to be 1 time. That's going to be 2 times. That's going to be 3 times. That's going to be my new A. Okay? Then B is going to be over 1 up 2. That's 1 over 1 up 2 over 1 up 2. And that's going to be my new B. And we're going to do that for each of these. C's, there's 1, there's 2, there's 3. There's my new C. And D is over 1 down 2, over 1 down 2, over 1 down 2. And that's going to be my new D. And when we connect those dots, you'll notice something about the new figure. Okay? And these are some of the questions we're going to answer now that we've done that. How are the 4 shapes different? I think that means to say 2 shapes, or maybe the 4 points. But what is different about these 2 shapes? Well, the lengths of the sides are different, aren't they? The lengths are different. What about, how are they the same? Aren't they the same shape? Doesn't one just look bigger than the other? What this would tell us is that the angles are the same. They all have this, all 4 angles still have the same measure. So when we're talking about dilation, does it preserve distance? Are the lengths the same length? No, it does not preserve distance. Does dilation preserve angle measure? We already saw that it did, yes. Is dilation a rigid transformation, meaning does it keep the same size and shape? The answer there is no. Remember, it did not keep the same size. It kept the same shape, though. Okay, looking at the second page of our notes, similar polygons, if they are similar, they have the same shape, but not necessarily the same size. The symbol for this, and this is what we use to write that, is that little similar symbol. Two plane figures are similar if one can be obtained from the other by similarity transformations. Similarity transformations is reflections, translations, rotations, and now dilations. Remember, these three had rigid motion. They were congruent. However, when we add dilations into the mix, they now are similar. Which side of ABCD corresponds to segment CB? If we're looking at this segment, okay, so which side of ABCD corresponds to CB? You have CB. This is the segment that would correspond to it. Now remember, though, we would have to make sure we put those apostrophes next to them to show specifically which rectangle we're talking about. Compare the lengths. Well, this length of the large rectangle is 8, and then the side is 6. The smaller rectangle is 4 and 3. Notice that the longer one is twice as big. 4 times 2 is 8, 3 times 2 is 6. How could you get the lengths from dimensions of ABCD? We would multiply by 2. Could you get the dimensions by adding the same amount? Well, no, because 3 plus 3, which would equal 6, would work. But then if we added 4 plus 3, that would not equal 8. It would equal 7, so that would not be correct. Next, let's look at that same rectangle. And we will erase... Whoops. We will erase... Well, no, we won't. Monica enlarged, so she has the original triangle. Now, instead of these lengths, for some reason I can't get it to erase right now, we have a larger triangle that Monica is going to enlarge. I'm sorry, not triangle, rectangle. She knows that AB, her new segment, which would be this one, is going to be 20 units long. So what are we doing to 4 to get to 20? What are we multiplying by? We are multiplying 4 times 5. That is my scale factor. That is how many times larger it is going to be than the original triangle. If she used a scale factor of 1, how will the new rectangle compare to the original? We would multiply each length times 1, which basically would end up giving us an identical rectangle. How would they compare? Well, it'd be identical. Or it would be congruent. Another way of saying that. Now, if she used a scale factor of 1/2, half of 4 would be 2, half of 3 would be 1.5. We'd end up with a much smaller, a smaller rectangle. So, how would they compare? It would be smaller. Key note here, if it's greater than 1, it's going to enlarge. If it's equal to 1, it's going to be congruent. If it's less than 1, it's going to make it smaller. Okay, and the last part of the notes. Here we have two triangles. What do we notice about AB and the pre-image? Well, if we look at these two segments, we'll notice one's longer than the other, but we'll also notice that they are parallel, aren't they? And if we noticed all the sides, those are also parallel. and the last one, we would see that they would also be parallel to each other, never intersect. They are parallel. Explain why congruence can be considered a special case of similarity. Well, we still have the same size and shape. And we also have a scale factor of 1. If you know that two figures are similar, you conclude that corresponding angles are congruent. That is absolutely the case, yes. If two objects are similar, then their angles, corresponding angles, are congruent. Now on the opposite side, if we have two triangles who are similar, can we say that the lengths of their segments are congruent? That is no. Remember, length is not preserved. Length is not preserved when we're talking about similar figures. Okay, now looking at some application here, we have a couple triangles here. Are these two triangles similar? The simple answer is no, because they look nothing like each other. They do not have the same shape. And size-wise, they're both 4 here and 4 here, but then here we have 3 and 1. To go from 4 to 4, we would be multiplying times 1. Well, 3 times 1, this would have to have a length of 3, which would be right here, in order for them to be similar, which it does not. So the answer there is no. These two figures, are they? Well, you'll notice that they are a diagonal length here, one diagonal, not one unit, just one diagonal. And you'll notice this one is 4 across, which if this one was 4, this one was 4, and this one was 4, these, on the other hand, are all one diagonal in length, which means they have a scale factor of 4. So since the scale factor is the same for all of them, then yes, those are similar. These two triangles, they are congruent, and remember that congruent triangles are similar. So yes. What would the scale factor be if they were congruent? Remember, if they're congruent, the scale factor would be 1. How about this one? What would the scale factor be here? Well, we went from the small square to the larger square. If it was getting bigger, then the scale factor would be 4, because it's 4 times as large. Okay, I will let you do the rest of those on your own. Here, what you're going to do is you're going to end up with, we're going to dilate the original triangle. We're going to come up with a new coordinate for A and B and C, noticing that we're multiplying the original x by 2 and the original y by 2. So 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 3 times 2 is 6, 4 times 2 is 8, 1 times 2 is 2. Graph these points. 2, 4, that's my new A. 6, 6, that's my new B. And 8, 2, that's my new C. Connect the dots, and I have my shape. Notice they are similar. What would the scale factor be? It would be 2, because we're multiplying it times 2. Number 8 and 9 are the same. Notice what is going to happen here. We're multiplying it by a number greater than 1, therefore it will be larger than the original. Notice this is going to have a scale factor less than 1, so this triangle is going to actually be smaller than the original. And I will let you do the last 3 problems and try and figure those out on your own. Good luck.